Welcome back to the Deep Dive. Today, we're tackling, well, maybe the biggest roadblock for truly personal AI, how much it costs just to have a conversation.
We're talking large language models,
Mhm.
LLMs. Everyone hears about the billions spent training them, right? But the real challenge, the thing that decides if they actually get deployed everywhere and feel instant to you, is inference,
Yeah,
using the model day to day.
exactly. These things have billions of parameters. Running them takes huge amounts of compute, and maybe even more critically, memory. If inference stays this expensive and slow, well, high-end customized AI just isn't practical for most uses.
And solving that means looking beyond the usual suspect, the GPU. It means we need some real architectural innovation, often in specialized hardware.
Which brings us right to today's focus, field programmable gate arrays, FPGAs, and a pretty radical architectural shift they enable called spatial acceleration. We're digging into how this approach, using a dataflow architecture, aims to really tackle that LLM efficiency problem.
Welcome to this deep dive brought to you by Generative AI Futures, brought to you by Byte Goose AI.
So our goal today, we're slicing through the tech talk in these sources. We want to give you a really clear picture of where FPGAs fit in the LLM world, why memory access is the real bottleneck, and how this spatial data flow thing is getting these huge speedups and, frankly, amazing energy savings compared to top GPUs like the NVIDIA A100,
Yeah.
at least in some very important situations.
Yeah, it's that classic engineering fight, isn't it? General purpose versus super specialized, raw power versus smart data movement. Let's jump into why this choice between like time and space in hardware design really changes everything for LLMs.
Okay, let's start with the scale because it really sets the stage. When you're talking models with, I don't know, 7 billion, 13 billion parameters, the demand on the hardware is just immense. And yeah, GPUs are the go-to right now for good reason.
Oh, absolutely. GPUs are workhorses. They're built for massive parallel stuff, perfect for training, perfect for crunching huge batches of data during inference. They're kind of the default high-performance tool. But for that back-and-forth interactive AI, they start to show some cracks.
Right. And you mentioned two main drawbacks for that kind of conversational use case.
Yeah, first, power. They drink electricity. Running big GPU farms 24/7 for inference. That's a massive ongoing cost. And second, they're not always great for low latency, small batch stuff. You know, the quick chat where you expect an answer now. Often, just setting up the GPU to do the work takes longer than the actual computation for one little token.
Okay, so the GPU is the powerful but maybe sometimes inefficient general tool. The FPGA you said is more like a custom tool. How does that give it an edge architecturally?
It's all about that fine-grained programmability. Unlike a GPU or an ASIC where the silicon is fixed, with an FPGA, we can literally rewire the hardware circuits down to the gate level. This lets us build a model-specific spatial architecture, optimized just for one specific task or even one part of a model.
And that custom building leads to efficiency gains.
Totally. Because it's bespoke, engineers can use really aggressive tricks that GPUs just can't easily do. Things like extreme low-bit quantization, maybe 4-bit weights, 8-bit activations, or custom number formats. This shrinks the model size way down and, crucially, cuts down how much data needs to be moved around.
Okay, so this specialization, this custom building, it leads us to this core choice, temporal versus spatial architecture. Two completely different ways to run a neural net on an FPGA. Let's start with temporal, the older way.
Right. Temporal is the traditional method, often done using something called an overlay. The idea is reuse. You design one sort of general purpose processing engine, a PE, and you use it again and again over time to run different parts of the network, different math operations.
And the no downside to doing things one after another like that.
It's all about the data flow, or lack thereof. So you run the query calculation on the PE. Where do the results go? Well, since the PE has to do other things next, those results often get shoved off chip into slow DRAM. Then when it's time to calculate the key, you have to pull that data back from the DRAM, this constant shuffling data on and off the chip.
That's the bottleneck.
That's the massive bottleneck. It kills performance with latency, and it burns a ton of energy just moving data. It's, a data movement nightmare.
Okay, so spatial acceleration is the attempt to break free from that nightmare using the FPGA's reconfigurability.
Exactly. The spatial architecture, or data flow architecture, flips the script. Instead of reusing one engine over time, we use space. We dedicate different PEs to specific jobs. One PE just does query, another just does key, another does the first part of the feed-forward network, and so on.
So you're literally building the assembly line on the chip. Each worker, Each PE stays put and does only its one task.
That's a great analogy. And the key is how they talk to each other. These specialized PEs don't need to go off chip much. They pass data directly between themselves using really fast on-chip connections called streaming buffers. Think of them like tiny high-speed conveyor belts, usually implemented as FIFO's first-in, first-out buffers or sometimes multi-buffers.
So PEA finishes its bit. The data zips straight to PEB through this fast lane, and PEB starts working immediately without that slow trip to external memory.
That's the huge win. You keep the data flowing on the chip, minimize the input-output, slash the latency. You get concurrent processing, like a pipeline where everything is happening at once across different stages. This shift from sequential temporal work to parallel, spatial data flow is really how FPGAs can start to compete with and sometimes beat high-end GPUs on speed and efficiency, especially for certain kinds of jobs.
But hang on. If you dedicate a big chunk of silicon to a PE that only does, say, the key calculation, and maybe that calculation is quick, especially in the later stages, isn't there a risk of that PE just sitting idle a lot of the time? Doesn't that waste resources compared to a GPU where the cores can be doing anything?
Ah, that's the million-dollar question, right? And it's the core trade-off the researchers wrestle with. It comes back to that fine-grained control. They can customize the size and the power of each PE. The goal is what they call work balancing. They try to design the pipeline so that every stage takes roughly the same amount of time to execute.
So no bottlenecks in the assembly line.
Exactly. If the pipeline is perfectly balanced, every PE is busy minimizing that idle time. That analytical model we'll get into later. A huge part of its job is figuring out exactly how to allocate resources to achieve that balance and maximize the use of all that specialized hardware.
Okay, so we have temporal versus spatial. Got it. But now we need to layer that onto how LLM inference actually works, because it's not just one thing, is it? It's two very different stages.
Yeah.
And the hardware needs to handle both or be really tailored for each one.
Yeah, the split personality is probably the central headache in designing any LLM accelerator, FPGA, or GPU. The way they compute, what slows them down, it's completely different between the two stages. Makes it really hard to find one design that's perfect for both.
All right, let's break it down. Stage one, the prefill stage. This is when I type in my prompt, right? A potentially long sequence of tokens? Anil input, what's happening computationally here?
This is where the model digests your entire prompt all at once. It processes everything simultaneously to figure out the context and generate just the very first word of the answer. And computationally, it's intense, really compute intensive.
And this is where the math gets scary, that quadratic scaling you mentioned. Explain that again.
Yeah, it's brutal. The key part, the attention mechanism, involves multiplying big matrices together, specifically inside the scaled dot product attention, or SDP. The number of calculations multiply accumulates, or MAs needed for this, grows quadratically with the length of your input prompt. The formula is roughly $8, where the prompt length in dollars is a model dimension.
Okay, so quadratic. If my prompt is twice as long, calculating that first word doesn't take twice as long, it takes 4 times as long.
Basically, yes. For long prompts, the compute time just explodes. You need massive parallelism to handle it. Now, for an FPGA, which typically has less on-chip memory than a big GPU, the main thing holding it back during this stage is usually off-chip memory bandwidth. Can you shovel the huge prompt data and all the model weights onto the chip fast enough to keep those hungry compute units fed, especially when they're facing that quadratic workload?
Right, makes sense. That's the big parallel crunch at the start prefill, limited by bandwidth. Okay, now stage 2, the decode stage. This is after the first word when the model is generating the rest of the answer one word at a time.
Exactly. Decode is sequential. It's autoregressive, meaning each new word depends on the one that just came before it. And this completely changes the computational picture.
It flips from being compute-heavy to memory-heavy.
Correct. Instead of processing a long sequence all at once, the hardware only processes one token at a time. So the number of MXEs needed for the core math becomes pretty much independent of how long the conversation gets. The calculation part is small, but fetching the needed data becomes the challenge.
And this stage lives or dies by the KV cache. You said this is super important for efficiency.
Oh, absolutely critical. The KV cache, key value cache. Remember how in prefill the model calculates key, K, and value V information for every single word in your prompt? Well, instead of throwing that away, it stores it in a fast memory buffer, the KV cache.
Why keep it?
Because when generating the next word, say word number 3, the model needs to consider not just word 2, but also word 1 and your entire original prompt. To do that efficiently, instead of recalculating everything, it just grabs the old K and V tensors from the cache and combines them with the K and V for the newest token.
Ah, so it avoids redoing all that work for the past context.
Exactly. It avoids tons of redundant computation, makes the sequential generation much, much faster, and drastically cuts down the number of MXEs needed per token.
So because this decode stage minimizes the compute and relies heavily on quickly accessing this growing KV cache, this seems like the perfect place for that spatial FPGA architecture to really shine. This is where minimizing memory overhead should be a huge advantage.
That's the theory, absolutely. But actually building hardware that elegantly handles both the massive prefill burst and the delicate decode sequence, it's tricky. The researchers pointed out two big hurdles they had to jump.
Okay, hurdle number one, the challenge of navigating diverse parallelism.
Yeah, it's a hardware juggling act. Your chip needs to blast through the prefill stage, needing huge parallelism across the sequence length. But then it immediately needs to switch gears to handle the decode stage, which is sequential and needs super low latency for just one token at a time. Designing an architecture that can efficiently switch between these very different modes is tough.
And the second hurdle sounds like a classic tech problem.
Yeah.
Software moves faster than hardware.
Pretty much. The lack of standard hardware building blocks. LLM designs are changing constantly, right? Think GPT-3, then Llama, Mixtral, whatever comes next. This super fast software evolution makes it really hard to develop standardized, reusable hardware components for FPGAs. It slows down the design process compared to, say, using standard CUDI libraries on GPUs, where the hardware is fixed and the software tools are mature. You end up reinventing wheels unless you build good, reusable libraries.
Right, so if you want to build this complex, specialized hardware
Yeah.
and actually have it work efficiently, you can't just start coding, right? You need a plan, a model. Which brings us to this analytical framework the researchers developed. This wasn't just for checking their work afterwards, was it? It was more like the blueprint.
Absolutely foundational, yeah. You need it to estimate performance, figure out that work balancing act we talked about, and critically predict if and when the FPGA can actually beat a GPU. FPGAs have hard physical limits, The model basically maps out those limits. The researchers boiled it down to four main constraints. Think of them as the rules of the road for FPGA design that dictate what's even possible for a spatial architecture.
Okay, constraint one seems straightforward. Compute resource constraints. Basically, how much math can you do at once?
Yep. DAGUN is the total number of max units, the calculation engines, on the chip. But in a spatial design, you're carving those up. So the rule is the sum of all the AMIC keys you assign to each specific job, query, key, value, the first matrix multiply, the FFN layer, etc., across all the parts of the pipeline you put on the chip, that total has to be less than a moment. You're physically dividing up your limited compute power.
Makes sense. Constraint two, memory capacity constraints. This is about storage, right? Especially for that KV cache.
Storage is huge. Can the chip actually hold everything it needs? That means the model weights, those intermediate streaming buffers, the FIFOs, and yeah, crucially, the KV cache. The dream for dataflow is to keep as much as possible in the fast on-chips RAM. If the total needed storage weights, cache, buffers is bigger than the on-chips RAM, well, your design either fails or performance tanks because you're constantly going off-chip to slower DRAM. And remember that KV cache often needs double buffering so you can read and write at the same time, making the capacity crunch even worse.
Okay, constraint three starts to get into the weeds of parallelism. Memory port constraints. Why are memory ports a bottleneck if everything's happening in parallel?
It's like too many people trying to get through one door at the same time. In a spatial design, you might have hundreds, thousands of mass C units running side by side. If they all suddenly need to read weights from the same block of on-chip memory or write results back, they have to queue up for the limited number of access ports to that memory block.
So they end up waiting, even though they could be computing. Idle time.
Exactly. Idle time kills your parallel speedup. So you have to manage that contention for ports.
How do they fix that? What are the solutions?
Two main ways. First, you can physically split the memory buffer into smaller chunks, each with its own ports, more doors, basically. But that uses up more silicon real estate. The second, often smarter way is data packing.
Okay, data packing. Explain that again.
So remember, they're using low-bit quantization, like 4-bit weights. Instead of fetching one tiny 4-bit weight at a time, they bundle several of them together into a single, wider chunk of data before reading it from memory. Say you need to feed 4 MC units working in parallel, each needing a 4-bit weight. Instead of 4 separate memory reads, you pack those 4-bit weights into one 16-bit word. Then, one memory read through one port gets you the data for all 4 units simultaneously. It's a clever way to get more data through the limited ports.
Nifty. Okay, and the last constraint, the one that really hits that prefill stage hard, memory bandwidth constraints.
This is the big one, when your model weights are just too large to fit on the chip and have to live in the main off-chip memory, the DRAM or HBM. There's a hard limit on how fast you can physically transfer data between the FPGA chip and that external memory. If the amount of data your design needs per second is more than the chip's maximum bandwidth, you're bandwidth bound.
Doesn't matter how many compute units you have on the chip if you can't get the data to them fast enough?
Precisely. The model calculates exactly how much bandwidth is needed based on things like the bit width of the weights, how many mechs are running, and how much data can be reused on chip. And this predicts that performance cliff where current FPGAs just can't keep up with GPUs in the prefill stage.
So, assuming the designers navigate these 4 constraints, the model then helps them with work balancing. Why is balancing the workload across the pipeline stages so critical for spatial?
Think back to that assembly line analogy. The whole line only moves as fast as the slowest worker. If your feed-forward network stage takes 50 nanoseconds, but the attention calculation takes 100 nanoseconds, your overall pipeline speed is limited to 100 nanoseconds per token. That FFN stage is sitting idle half the time. Huge waste.
So the goal is to tweak how many compute resources, how many valued units you give to each specific job, query, key, value, attention, FFN, until they all take roughly the same amount of time.
Exactly. You want every stage to finish its work just as the next piece of data arrives. This gets you to a sort of global compute power dollar for the whole pipeline. The researchers showed that if you achieve this perfect balance across $1 and fiber cores, the prefill latency ends up being proportional to $1 plus 1C AD2MM.
Wow, okay, that formula really ties it all together. Latency goes down if you increase the balanced compute power or put more layers on the chip, but how much dollars you can actually get is limited by those 4 constraints we just talked about.
It's a complete feedback loop. The model helps you tweak the knowledge for each stage, checking against the constraints, iterating until you find the sweet spot, the fastest possible balanced pipeline that fits within the physical limits of the chip. Honestly, trying to design a high-performance spatial accelerator without this kind of rigorous modeling would be like flying blind. The complexity is just too high.
Okay, the analytical framework laid out the what's possible. Now let's get into the how they actually built it, the hardware implementation. This is where the FPGA's programmability really gets put to work, right?
Yeah, this is the engineering craft. Their strategy was all about efficiency and, importantly, being able to reuse their work. They built a library of high-level synthesis HLS kernels. Basically, they wrote C++ code that describes the hardware components. This lets them generate the hardware for different transformer models like BERT or GPT much faster than writing low-level hardware description languages.
And for the heart of the LLM, those huge matrix multiplications, the linear operators, they needed a specific structure to get maximum throughput and data reuse to avoid moving data unnecessarily.
Right. They went with an output stationary systolic array architecture. Okay, that's a mouthful. Picture a 2D grid of MAC units. Systolic means data pulses through this grid rhythmically, like a heartbeat, synchronized by the clock. Output stationary means the intermediate result for a specific output value stays put in one calculation unit, PE, while the input data and weights flow past it.
So by keeping the output calculation in one place, they're reusing those intermediate results locally in that PE's little cache instead of shipping them across the chip. Cuts down latency and power.
Exactly. It's designed to maximize local data reuse and hit that peak global compute power that the model said was possible. Now, okay, probably the cleverest bit of hardware optimization in this whole thing, DSP packing.
This sounds like getting more bang for your buck from the hardware blocks.
That's precisely it. FPGAs have these specialized blocks called DSPs, digital signal processing blocks, like the AMD DSP-48-2. They're built for fast math, often handling big multiplications like 18 bits times 27 bits. But remember, the LLM design here uses W4A8, tiny 4-bit weights and 8-bit activations.
If you used a whole big DSP block just for one little 4x8 multiply, you'd be wasting almost all of its capability.
It's totally wasteful. So they figured out DSP packing. They realized they could cram 2 4-bit weights and 1 8-bit activation into the inputs of one of those big DSP blocks. They do a single combined multiplication, which gives a big 45-bit result. Then, and this is the magic, they carefully slice up that 45-bit result to pull out the answers for two separate 4x8 multiplications.
Wait, hang on. One big multiplication gives them the result of two smaller, independent multiplications.
Yes, they exploited the internal structure of the fixed-point DSP block to effectively run two MSC operations in parallel using just one physical block. This trick instantly doubled the number of logical MS units they got from each physical DSP slice. If the FPGA has, say, 2,000 physical DSPs, suddenly they have 4,000 effective MSC units doing the work. It's pure, fine-grained hardware optimization to boost density and save resources.
That is seriously clever hardware hacking.
Yeah.
Okay, beyond the big linear math, what about the other functions? Softmax, GLU, the nonlinear stuff.
Right, those are crucial too, but they're tricky because aggressive quantization can really hurt the model's accuracy there. So they kept those parts running in floating point for better precision. The key design point, though, was making sure these blocks could process data row by row and slot neatly into the main spatial pipeline. They had to ensure these nonlinear parts didn't become a bottleneck and stall the whole data flow.
We touched on quantization being a key efficiency tool earlier. What were the main takeaways about quantizing weights versus activations?
Yeah, Insets 3 and V really hammered this home. Weight quantization is essential. Dropping weights down to 4-bit or even 2-bit drastically shrinks the model size. And the huge benefit is reducing the off-chip memory traffic that prefill stage killer. Less data to move means faster loading. The sources actually said 2-bit weights gave like an order of magnitude speedup compared to 16-bit.
But interestingly, they found quantizing the activations didn't help much in this specific spatial architecture.
That was Insight 3. Because in this dataflow design, the intermediate activations zip directly between PEs through those fast on-chip FIFOs. They don't really get stored in big on-chip memory buffers. Since the activation movement is already super optimized, making them even smaller with quantization didn't give much extra benefit in performance or resource savings here.
Okay, last big piece, scale. Models like Vicuna 13B are just too big for one FPGA, even a beast like the Alveo U280. How did they spread the work across multiple FPGAs?
Yeah, you need distributed inference for that. They use tensor parallelism, or TP. Think of it like splitting a giant work project across multiple team members. You chop up the model's parameters, like the big weights and the feed-forward network layers, and give each FPGA a piece. Each FPGA computes its part of the result.
But then you need to combine those partial results from all the FPGAs to get the final answer for that layer, right?
Exactly. That requires a communication step called entextual reduce. Everybody shares their partial result and combines them. TP usually needs 2 of these all-reduced steps per transformer layer. The potential problem is waiting. If FPGA-B has to wait for FPGA-A to finish and send its data before it can proceed, the pipeline stalls.
And their trick was to make this communication non-blocking.
Yes. They designed a non-blocking textual reduce. This means an FPGA can start adding incoming partial results from its neighbors as soon as the data starts arriving. It doesn't wait for the entire message. This keeps the data flowing smoothly across the different FPGAs, minimizing synchronization delays and preserving that low latency pipeline even when distributed.
And even within one FPGA chip, like the U280, they had to manage the layout carefully because it's made of multiple pieces of silicon.
Right. The U280 has 3 sections called super logic regions, or SLRs. Even using HLS, they had to manually plan the physical layout, put the Q, K, V parts on SLR0, the attention and output math on SLR1, and the FFNs on SLR2. This careful physical placement across the chip was vital to manage power, avoid signals traveling too far, which causes timing problems, and actually get the design to meet its speed targets. It really proved why that analytical model was needed to guide the physical layout too.
All right, the moment of truth, the performance results, all this fancy architecture, modeling, optimization, did it actually pay off against the reigning champ, the NVIDIA A100 GPU? And crucially, how did it look across those 2 different inference stages?
Let's start with the tough one for the FPGA, the prefill stage. Remember, compute intensive, that nasty 2D scaling.
What does the numbers show?
Insight, I was pretty stark. Current FPGAs just aren't as good here. The A100 GPU basically held a flat, super low latency until the input prompt got really, really long. The FPGA's latency, though, it climbed pretty much linearly with the prompt length. It just couldn't keep up with that compute burst.
And we know why from Section 3, but let's nail down that core reason again.
Insight 2 confirmed it. It's overwhelmingly about getting the parameters from off-chip memory fast enough that memory bandwidth constraint. GPUs like the A100 have massive HBM2B memory bandwidth. They're physically larger, they just suck in data way faster and handle that quadratic compute load better. The researchers calculated that for an FPGA to just match the A100 on prefill, it would need something crazy like 30,000 MSEs per cycle, and assume you magically solved all the memory bottlenecks. It really shows the current hardware gap in bandwidth.
Okay, so GPU wins round one, processing the initial big prompt. But then the tables turn completely for the decode stage, right? The word-by-word generation.
Totally flips. This is where the FPGA's spatial architecture was designed to win, and it did. Remember, decode is sequential, memory-intensive, relies on that KV cache. The GPU, being general purpose, actually struggles here. Its massive compute resources are underutilized, and its memory system creates overhead for these small, sequential accesses.
But the FPGA's data flow, minimizing off-chip trips, optimized for this exact kind of low-latency sequential work. It should be perfect. What were the actual speed-up numbers?
Get this. The spatial accelerator on the FPGA was 1.9 times faster than the A100 GPU during the decode stage for GPT inference. That's huge. It means the FPGA is significantly quicker at the very task that defines the feel in a real-time conversation.
Wow, nearly twice as fast. And the energy efficiency, that's often the bigger story for running these things at scale.
Even more dramatic, the FPGA accelerator used 5.7 times less energy per token than the A100 in the decode stage. 5.7. And think about this. The FPGA they use, the Alveo U280, is on an older 16-nanometer process. The A100 is on a much newer, more efficient 7-nanometer process.
So architecture beat process technology.
Absolutely. It proves that smart, specialized architecture can overcome a disadvantage in the underlying silicon manufacturing process, delivering massive efficiency gains.
And this strong result also validates the whole approach, including that analytical model they built.
It really does. The performance predictions from their model were remarkably close to the actual hardware measurements. Like, for the GPT prefill stage, their estimate was within 92% accuracy. That shows the model isn't just theoretical, it's a practical, reliable tool for designing these complex accelerators.
And finally, scaling it up. Did the multi-FPGA setup deliver on its promise for huge models?
Yes. Insight Seconder showed that using tensor parallelism across multiple FPGAs, 2, 4, or 8 of them, combined with that crucial non-blocking communication, significantly cut down the overall latency for big models like Vicuna 13B. It demonstrates a viable path for deploying even very large models efficiently using these specialized FPGA platforms. #tag outro.
So wrapping up this deep dive, it seems like we have a really clear picture now. The core achievement here is that this spatial data flow architecture on FPGAs offers seriously impressive efficiency for the decode stage of LLM inference, the part that's memory-bound and needs low latency. By building that custom assembly line on the silicon, they slash memory overheads.
Yeah.
It makes FPGAs the clear winner for the actual sequential conversational part of AI.
But the flip side is also clear. That initial prefill stage, the compute-heavy part, is still hampered by the memory bandwidth limits of today's FPGAs. And this really frames the big questions for the future of AI hardware.
Yeah, like what will the next generation of AI-focused FPGAs look like? If the vendors can dramatically boost memory bandwidth and make the on-chip connections even faster, could FPGAs finally close that gap in the prefill stage too? Could spatial acceleration dominate the whole process?
That's the multi-billion-dollar question for FPGA makers for sure. But there's another, maybe even more practical challenge for the whole industry right now: heterogeneous deployment. What we've seen is that GPUs and FPGAs have very different strengths, almost perfectly complementary, right? GPUs crush the prefill compute. FPGAs excel at decode efficiency and low power.
So why pick just one and compromise?
Exactly. It seems increasingly likely the future of running large-scale LLMs won't be just racks of GPUs or racks of FPGAs. It'll be smarter, mixed systems. Maybe the initial prompt goes to a GPU cluster for that prefill burst. But as soon as that first token is generated, the task instantly switches over to an FPGA cluster optimized for efficient, low-latency decode.
A hybrid system.
Yeah.
Using the absolute best tool for each specific part of the job, maybe even switching dynamically. And that's a really interesting path forward. It can make powerful AI much more efficient and accessible.
It definitely paints a picture of a more nuanced, optimized hardware future. Thanks for joining us for this deep dive into spatial acceleration.
We'll see you next time on The Deep Dive.